So today I'm going to tell you a little bit about some of the work we've been doing here at Cooper Genomics to look at PGT-A, formerly PGS. So this is the technology that we've been developing here to try and improve the quality of this technology and try and bring some new benefits, features and benefits to our IVF customers and hopefully our patients. The talk will really be split into 4 parts. The first part is just a little recap as to why we're here doing PGT-A. Fairly simple, fairly straightforward. The second part is to tell you about our technology that we're using right now for our customers. That's PGT-AI, AI standing for artificial intelligence. I'll go through a little bit about that and look at the results we've had since we launched that technology 10 months ago. Then I'll go on to tell you a little bit about the technology that we have developed and we're releasing next week on September 3rd. So all samples that are sent to Cooper Genomics from September 3rd will be on our new technology, which is PGT-AI 2.0. And finally, we'll hopefully have some questions. And if you have some questions, don't be shy, send them through the chat area and we'll try to get your questions at the end. This webinar is being recorded and you'll have the opportunity to get the recording should you wish as well. Okay. So Cooper Genomics, we've been around in this area for as long as this area has existed for pre-implantation genetic testing. So the very first PGT-A, PGT-M case, as we used to know it, PGD, was done by one of our founders. The very first PGT-A, or PGS as we used to call it, was done by one of our other founders. And we've done more than 500,000 procedures in PGT over the years. So we clearly have the most experience in this area. And what we're trying to do is trying to now push the technology and use our experience and use our knowledge to see where we can go. So this talk is going to be about PGT-A, pre-implantation genetic testing for aneuploidy. It's simple. It's counting chromosomes in embryo biopsies. And that's what we do. And we're trying to improve the technology and trying to push this technology as far as we can. So just as a little aid memoir for me here, there are 3 areas of PGT. I'm going to talk almost exclusively about PGT-A, aneuploidy testing, as it was known before, PGS, CCS, a bunch of other acronyms. That's screening for chromosomal abnormalities in embryo biopsies. It's an option to all IVF patients, and there are some really good data that have just been coming out from SART and some other areas that shows it improves IVF success rates even per intent to treat. I'll not talk about that data, but that's some really cool data that might be in a subsequent webinar. PGT-SR is similar but different, and that's where you know that the couple coming in are carriers, one of them usually of a chromosomal rearrangement. So you're looking for changes in the chromosomes associated with that chromosomal rearrangement, because if you get an unbalanced embryo, then it's very, very likely to end up in a miscarriage. So the technology I'm going to talk to you today about, PGT-AI and AI 2.0, is essentially what we're going to use for PGT-SR, except with SR, we just need some additional information for the chromosomal rearrangement that the couple have. What I'm going to talk very little about is PGT-M, or as we used to call it, PGD, except to say this is a technology that we've been using for many, many years, and we use a technology called SNP arrays for this, and I'll come back to that later on in the presentation. So again, this is kind of like a memory slide for me, because it's to remind me that what we do is not in isolation. What we do is associated and in collaboration with IVF clinics, embryologists and doctors. So in order to have the PGT-A process a success, you need good quality IVF, you need good quality embryo biopsy, you know, without good quality embryo biopsy, what we do is not quite meaningless, but is very difficult. You need vitrification, and only once you get to this long part of the process does the sample come to the lab for us, and we try to get results wherever possible, and then give you the results, and hopefully you can then make a decision on which embryos to transfer. Cooper Fertility and Genomic Solutions, although I'm talking just about the genomics today, obviously can help from the IVF process, embryo biopsy. We have great embryo biopsy workshops in our Center of Excellence in Livingston, New Jersey, and the whole process there. But let's stick to PGT-A. So the premise of PGT-A is fairly simple. If you have an embryo biopsy with the correct number of chromosomes, that's 46, that is called euploid. If you implant an embryo with that correct number of chromosomes, it's likely to have a higher success rate than one with the wrong number of chromosomes. Now, even implanting euploid embryos doesn't guarantee success, but randomized controlled trials and the analysis of SART data shows that it does improve outcomes. If you have the wrong number of chromosomes, and this is a fairly simple example, you can see here we have 47 chromosomes in this embryo biopsy. So this is a meiotic error. This occurs in the egg or the sperm. All the cells have one extra chromosome, and in this instance, a chromosome 10. Now, 47 triple 10, I can tell you as a cytogeneticist, there's never been a healthy live birth with that cytogenetic abnormality. So you know if you put back that embryo, it's not going to succeed. So it's screening, and we're screening for the correct number of embryos. And aneuploidy, as we know, increases with maternal age, and it's one of the main causes of infertility. So we're trying to avoid those aneuploid embryos, particularly with advanced maternal age. And if you implant those aneuploid embryos, they will result quite often in failed implantation. There's a huge amount of data now that shows that you have increased miscarriage rates with aneuploid embryos. And finally, it can cause genetic disease. So if you implant an embryo with trisomy 13 or trisomy 18 or trisomy 21, you'll get a genetic disease like Down syndrome, Edwards syndrome, Pato syndrome. So that's the premise. And up until a few years ago, it was fairly simple because we were saying gain an extra chromosome or lose a chromosome, that's bad. However, technology has moved on, and our understanding of embryo biology has moved on. And now what we're seeing is embryo mosaicism. Now, this is probably a whole webinar on its own, and we will probably come back with a webinar on mosaicism in the future. But what happens in mosaicism simply is you have two or more cell lineages in an embryo. You can see here on the left, you have an embryo which has euploid cells in green and aneuploid cells in blue. And on the right, a slightly different one, aneuploid cells in blue, euploid cells in green. And if you take that biopsy, you now have to not just count whether there's a gain or loss of chromosomes, you have to count whether there's partial gains or losses. And that's more challenging for us doing the genetic testing, and we've had to improve our technology to be able to do that. Mosaic embryos, though, are really interesting because there's been a sort of small but growing amount of evidence that show that they implant less, they miscarry more, and they can sometimes lead to live births. So sometimes, you know, you might not, if you have no euploid embryos, you might not want to discard a mosaic embryo, but consider whether it's something suitable to transfer, because many centers are now seeing live births after mosaic embryo transfer. And what we're trying to do is improve the information that we can give about levels of mosaicism as well. What I would say is, though, mosaicism does occur naturally, and some of us out there probably are mosaic. So the PGT-A results that we generate are in 4 classes. What used to be nice and simple as euploid, aneuploid. If the lab wants to know, we now will tell them whether they're mosaic. So euploids, all the chromosomes are normal, high chance of success rates. Aneuploid, all the cells are abnormal, and it has almost no chance of a healthy live birth. In between, you can get mosaics, low level and high level. Low level, we class it here at Cooper Genomics as 20 to 40% abnormal cells, and high level, 40 to 80% abnormal cells. And what we see is with the lower level mosaic biopsies, they have not such a good outcome as a euploid, but better than high level. On the high level, have a better outcome than aneuploid, but worse than the low level mosaics. So we're trying to give the clinic the best chance of finding a euploid or finding a mosaic to give the patient the maximum chance of getting something to transfer. So this is kind of where we were up until less than a year ago. We were using technology that was originally developed, and I was one of the people that developed this back in the day. But this technology was released back in 2014, and here we are in 2019. And just to kind of give you some kind of comparison, this is back in 2014, we were iPhone 5s. Now we're iPhone 10s and iPhone X, and the technology has moved on. 5 years is a long time in a high-tech area, and we were fixed on a test, and what we've tried to do is develop our own custom test that enables us to do more things in a different way. And this is the test that we've been running since November 1st last year, and this is PGT-AI. AI standing for artificial intelligence. So it's been a groundbreaking platform in pre-implantation genetic testing. It's a first of its kind mathematical algorithm, and it allows us to harness big data and artificial intelligence and machine learning to try and improve our results, to reduce noise, increase signal, and that maximizes sensitivity and specificity. And I'll go on to explain that a little bit in a minute. When we say big data, we're doing tens, if not hundreds of thousands of embryo biopsies, and we're getting hundreds of thousands of next generation sequencing reads. So we're talking about data in the billions of data points, and that's where you can start to use the power of this kind of technology. So what this did, it enabled us to go back and think about how we were actually doing PGT-A and how we're using the technology, and try and go back with a clean sheet of paper and see how we could improve the technology. And what we did was different from what the softwares that have been used in the past were doing. So you have to take something as your baseline in this technology, and you have to use that as a baseline for normal, and then you can call abnormal from that. And previously, software, including the software that I've developed in the past with various teams, we used cell lines, and cell lines obviously aren't embryo biopsies, and they were quite small cell line cohorts. What we did was we took embryo biopsy data, and for our baseline, we said we want embryo biopsies that resulted in live births and sustained pregnancy outcomes. And that became our baseline for the AI algorithm. And then we validated using sequencing data from 10,000 embryos. And the poor guys in R&D looked at that manually and looked at it via AI. And the AI did about 7% better in accuracy of calling. So what this has allowed us to do is, for the first time, go away from manual subjective interpretation and just use statistical calling for PGT-A. And that is robust because you get the same calling every time, and it's accurate because you get the same calling every time, and it removes subjectivity, and avoids other errors in the process. So just to kind of give you some sort of idea how this works. So back in the past, we'd receive a biopsy from an IVF clinic. We'd amplify that DNA about 1 million times. Then we'd put that DNA onto a next generation DNA sequencer, and we would end up with a number of sequence reads, and we take that and strangely convert it into an image. And you see an image that goes up and down for gains and losses. And some of our scientists would then have to go through each one of these images and call a gain or loss. And we'd have to have 2 initial independent scientists and then a 3rd independent scientist to look at the 2 independent scientists, and then we'd have to put it into a report. And you can see that is a pretty high human endeavor kind of exercise. And, you know, we do our absolute best, but, you know, there is a possibility of risk of getting that wrong. Also, it's a bit like embryo biopsy grading. You know, each person might have a very slightly different view of an embryo biopsy grade. And for me, I used to think of it as like the pessimists and optimists. Somebody had come in, the optimist, and go, yeah, I think that's normal. I really want to give them the best chance of having a euploid embryo for transfer. Another person come in, I can see a tiny blip there. You know, maybe that's something that we need to call. What we do now is we don't look at images. We just use the stats to give us the results. So we do exactly the same process as before. We do the DNA amplification, we put that on the DNA sequencer, and now it's the AI algorithm that counts the chromosomes, that looks at the 1,000 human biopsy samples for the normalization, that produces the reports. And it enables us to use big data and avoid subjectivity. So what I'm now going to tell you a little bit about, and please, if you have any questions, add them into the chat room and we'll try to get to them at the end. What I'm going to tell you about now are some of our observations from this platform, released 10 months ago, not quite 10 months ago, and what we saw in the first 6 months of using this compared to the previous 6 months using the, or 10 months using the subjective old technology. So the thing that's been really interesting is with this system, we've been able to reduce the noise, improve the signal, and make things much more consistent. And that's resulted in more euploid embryos being reported, an increasing number of patients with at least 1 euploid per cycle. And just to put that into a number context, in the first 6 months, that was 1,300 more euploid embryos being reported, which is really good because that gives our clinicians and IVF labs the chance of having more embryos to transfer for patients, which is our aim. So if you look at the numbers, because the numbers are pretty interesting, and it tells you a little bit about how this has worked. We see a 7.7% relative increase in euploid embryos. So it's not 7.7% of all embryos, but say you have a 50% embryo euploid rate. 7.7% would be a 3.85% increase in total numbers, or 7% relative. So we're seeing maybe 3-4% of embryos that are now called euploid that wouldn't have been out of the total. Where do they come from? Well, because we have a much better idea of the noise, we see a reduction in mosaic embryo reporting. And 21% sounds like a big number, but we only ever had about 10% of embryos that were mosaic. So it's 21% of 10%, so about 2% of embryos. And again, we have a reduction in aneuploid, and these are the ones that were aneuploid and now generally called high-level mosaics. So in all 3 categories, we're seeing changes. If we break that down by different groups and ages, we can see how that works. So in green, we have the changes in relative numbers of euploid embryos. In purple, the changes in relative numbers of mosaic embryos, and in blue, the relative number of aneuploid embryos. And you can see overall, we see that change of gain of euploids, loss of mosaics, loss of aneuploids. And interestingly, you see that gain in the number of embryos called euploid generally decreasing with age, and that's just because there's less and less embryos that can be called euploid with age, because most of them are clearly aneuploid. Donors, interesting. We're not really sure why there's a difference between donors and the under 35s, but it's something we're looking at right now. The other one, which is pretty cool, is seeing how many cycles have now have a euploid to transfer where they wouldn't have been. So it's about 4% of overall cycles that have now one euploid available for transfer. So it's about 1 in 25 cycles, but still a pretty good number and very much statistically significant. So this is PGT-AI, and this is what we've been running for the past 10 months. But when we started doing PGT-AI, we knew it wasn't the start of what we were doing, because as soon as we moved from our old technology, we're able to move on and not just change the way we do our analysis, but change the whole way we do our next generation sequencing. Previously, we'd use small sequencers. Now we've moved to the big generation sequencers. It gives us a lot more options to the way we can do PGT, and hopefully improve the results for our clinics and subsequently our patients. So PGT-AI 2.0, it still uses PGT-AI, the algorithms built on the biopsy data from 1,000 live births, highly validated. But now we have 10 times more sequencing. So to give you some kind of indication, that's 10 times more than anybody else, and up to 50 to 100 times more sequencing than some other labs do. So pretty huge amount of sequencing. Not only have we improved the amount of sequencing we've also improved the way that we sequence. And now, instead of reading the sequence once, we read the sequence from both ends of a DNA molecule, and that tells you exactly how big the molecule is and where it is in the genome. So whether it was unique from the embryo, because one of the things you sometimes get is duplication in the whole genome amplification or duplication in the sequencing. So this is a real cleaning up the noise of the PGT-A that we're able to do with this sequencing technology. That's really cool. The other thing that we're doing is adding SNPs to our test. Now, if you remember back at the very, very first part of this presentation, I said that we were using PGT-M for a lot of tests, and we use SNPs. So the way that we use SNPs back in PGT-M is using a technology called SNP arrays, which is quite an old technology, but really good. And it's really good for following the inheritance of chromosomes through generations to avoid affected chromosomes. And also, when we've been doing PGT-M in the past, we split samples and we do PGT-A and SNP arrays. But what we wanted to do with this technology, and the real key here, is we wanted to combine these technologies together, SNPs and copy number counting using the DNA sequences, to give the best possible tests. That's a real tough challenge, because generally to do SNPs using sequencing, you need to do a really focused amplification to get the coverage. And doing global coverage of SNPs at the amount we sequence, well, there's a lot of papers that are out there that discuss this. All those papers tell you that you can't do it. But we have found a way to do it, and now we have a test that has now 2 completely independent methods for aneuploidy detection and calling. A primary method of next generation sequencing and a secondary method of SNPs. This is PGTi 2.0. So it has clearly benefits that it's two independent methods for calling abnormalities. The conversations about artifacts and is what you see an artifact of the PGT-A processing is really killed off with this independent methods. It also, as an aside, lets us analyze all forms of ploidy, haploidy. Previously, we've been able to do male triploidy using NGS, but also now female triploidy. And I'll talk about it in a little while, the origin of the aneuploidies, whether they were maternal or paternal. So just to give you a little bit of a background, a SNP is a single base pair change, and they occur all the way through our genomes. We're looking at probably between 4 and 5 million in each one of us, and they result from natural variation and evolution and reproduction. And the majority of SNPs have no effect, but they are the things that make us slightly different. And you can see on here, the top strand is a TA, the bottom strand highlighted in blue is a GC, and this is a single base pair change. We call them SNPs, or sometimes single nucleotide variation, SNP. And this is what we're able to now measure with PGTi 2.0. So we have unique patterns from mom and dad that are mixed together in the embryo biopsy. And you have what is known as A and B, which are the major and minor alleles, the higher and lesser frequency of each SNP. And without going into too many details, we're able to use the global assessment of SNPs to look for things like where we only see one SNP, monosomy, or 3 SNPs, trisomy. Now, we are releasing this technology next week on the 3rd of September. We have a white paper coming out, and we will be announcing the white paper and some more of the details of this technology at ASRM. So please come and see us at ASRM. So although we don't actually look at the graphs anymore for PGT-A, it's all statistical, it's kind of nice just to show you some graphs, just so you can get a little visual interpretation here. So on the left here at the top, you see a copy number counting using sequencing. So this is just putting the reads from the sequencer in to see how many samples we have. On the left, you can see there's a partial chromosome gain, and on the right, a full chromosome gain. And below, the same DNA, but run through our global SNP counting. And you can see on the left, it also shows the segmental change, and that's different because this SNP technology has the same resolution as the NGS and a chromosome change. So combining these two together, primarily analysis by CMV, secondary with SNPs, we have a joint aneuploidy assessment. We can remove artifacts. We have a 5 megabase resolution and a best-in-class mosaic calling. I see there's some questions coming through, which is great. If you have any more questions here, please send them through now. In addition to the test that we have, we also have an optional additional test. And if you remember, I told you that SNPs were really good at following the inheritance of chromosomes, whether that's for PGT-M, but also we can use it here to look for the origin of aneuploidies. Now, this is an optional extra test, and we call it PGTai 2.0 plus. You need parental swabs from mom and dad, and those samples, those swabs can be sent to the clinic or the patient. It is an additional cost, but it can be done as a reflex test. It doesn't have to be done when the 2.0 test is done. It can be done retrospectively, and it can be done at any point after the 2.0 test. The reason why we've done this is because there's some interesting things you can do with looking at the inheritance of aneuploidy. So this is to look to see where the aneuploidies come from. Meiotic, whether it's whole chromosomes, or meiotic, whether it's segmentals. It's important that we can do smaller stuff as well as the whole chromosome stuff. The whole chroma stuff is primarily maternal, over 90% of the time. And you can generally tell just by looking at the maternal age how much aneuploidy is going to be maternally derived. But even so, there's still some value that sometimes it could be paternal, an indication of male factor. The one that's more interesting is really the segmental aneuploidies, because if you see quite a lot of these, we should, really look at these, because for the first time we've seen a genetic chromosomal change in embryos, which is majority paternal. And these segmental aneuploidies could be a real indication of male factor. So they are a useful thing to do them. Additionally, parent of origin is useful for the couples, just because you might have a cycle with no embryos to transfer, and it gives patients closure, or it helps decisions for things like gamete donation. So we've added that as an additional test. So in kind of conclusion of PGT-A 2.0, it's this combination of using sequencers to copy count chromosomes, copy number variation, and also using sequencers to look for SNPs and add these two together as two independent assessments of ploidy. We're able to do that because we now generate 10 times more data than we did before. It detects all forms of triploidy as well as haploid and some forms of other ploidy. It allows for parent of option testing, and it really bolsters the embryologist's 2PN validation, because it will see all forms of ploidy. So just to also say, we're not just here for the pure testing, we're also here for support and quality assurance. One of the things that we've been doing with PGT-AI is clinical report cards. So if you're a Cooper Surgical customer, we will look at your euploid rate. We will give you results, if you want, per clinician, what their euploid, aneuploid rates are. We'll look at mosaic levels, and we can also compare those results from a single clinic with the global Cooper Genomics results. Is a really nice little QC step. We also offer genetic counseling. Now, that's not something we routinely offer for PGT-A, but obviously the test is becoming a little bit more complicated, and we'd be happy in many circumstances to try and assist very much more if you want to know about PGT-AI 2.0 through your patient results. We also have a very cool technology called Engaged MD, and this is a tool that patients can use online before they come to the clinic to give them some sort of introduction to the area and help with many of the difficult questions that they might come up with. Finally, although we've authored many scientific publications and abstracts, we're always open to partnership and collaboration, and we'd love to be in touch with you if you want to find out more about PGT-AI 2.0. So that just really sums up this webinar. My name's Tony Gordon. I'm Vice President of Cooper Genomics. My email address is tony.gordon@coopergenomics.com. If you have any questions from the webinar that you might think about afterwards,